And welcome to a video on electronic configurations and doing electron configurations for atoms and ions. Electronic configurations help us with a variety of things, and it really is prerequisite knowledge for several other concepts that we'll get to. There are rules for doing them, and I'll start out by essentially drawing out with the arrows and all of that so that you understand better the periodic table method and other methods for doing electron configurations. Now, when we're writing an electron configuration for an atom, the number of electrons equals the number of protons. So we look at oxygen, for example. On the periodic table, it has 8 protons. Therefore, it will also have 8 electrons. So I'm going to draw 8 arrows on this energy diagram that I've sketched. Now please understand, this is a rough sketch, so it is not to scale. Alright, so I'm going to draw 1, 2. These 2 arrows represent the first 2 electrons for oxygen. So for oxygen's electronic configuration, it starts out with 1s2. I use a superscript 2 to say there are 2 electrons in that 1s orbital, subshell. Then, let's see, 2, 3, 4, so 2s2. Now I have 2p and I have 3 degenerate levels. These are equal energy. So I fill across them first. Let's see, I'm up to 7 now. And then I come back and double up. Why do we do that? Because that's Hund's rule. Alright, so I know there's more explanation, but this is a short video. Then I have 2p4. So my electron configuration for oxygen is 1s2, 2s2, 2p4, and I double check my answer to make sure that these exponents here, that they add to 8, and they do, so I'm pretty sure I'm okay. That's a way to check my answer. Now I can also write the shorthand notation. For the shorthand notation, I separate the core electrons from the valence electrons. This becomes very important for Lewis dot structures. So the shorthand notation, the core is going to be the noble gas that's 1 row up. I look at oxygen on the periodic table. 1 row up, the noble gas is helium. Helium has 2 electrons. So I take out the 1s2, that's the core electrons. That leaves 2s2, 2p4. And that's the electron configuration for oxygen in the longhand and the shorthand notation. Now what if we do this again for oxygen ion, oxide? The oxide ion still has 8 protons. If we change the number of protons, we change what element it is. So it still has 8 protons, but now it has a 2- charge, so it has to have 10 electrons, because 10 negatives plus 8 pluses gives you a 2- or a -2. Now I'm going to fill in 10 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Now I write it out. O2- is 1s has 2, 2s has 2, a maximum of 2 electrons per line. That's one of the rules. Not 3. Let's see, 1s2, 2s2, 2p6. Now when I write the shorthand notation, I have 2 options. I can write according with the He as the core, or since it has 18 electrons, the noble gas argon has 18 electrons. Therefore, O2- has the outside stability for its electrons the same as argon. This explains why O2-, the 2- charge on oxygen, is the most stable ion for oxygen. In the next videos, we'll talk about the triangle method and the periodic table method for doing electron configurations. Hope to see you there.